studying the Higgs boson. Start with the kind of canonical picture on the left-hand side. So you've all seen this on posters and t-shirts and what have you, the standard model set of particles. These are fundamental particles, point particles, consisting of fermions and leptons, fermions and bosons. So inside the fermions, you've got 3 families of quarks, and inside the lepton, for each of those 3 families, you have quarks and leptons. The universe is entirely made of up and down and electrons, right? The rest of the stuff is like just kind of old relics of the Big Bang that every once in a while we produce in a really high collision or a cosmic ray, but for the most part, they've been dormant for a very long time. On top of that, and can you guys see me, by the way? Well, you see my slides, but you also see me? Okay.
Yeah.
Because then I can talk with my hands and stuff. Okay, so you also have the force carriers, right? The gluon, the photon, Z boson, W boson. The gluon is the mediator of the strong force. The photons, Z and W, are electroweak. And then we have a new force recently discovered, which is the Higgs boson. And that's the thing that gives everything mass. So if you're pushing something heavy in space, it's heavy because the Higgs field is acting like a big molasses to slow stuff down. It's not enough, of course, to take a look at just these particles and say, this is what everything is made of. There is interactions and actual kinematics between them, which we define via a Lagrangian, which is on this ridiculous person's t-shirt, right? So this is the entire Lagrangian spelled out to about as long as you can to make an obnoxious t-shirt. And this is not the kind of Lagrangian I like to think of. The kind of Lagrangian I like to think of sits on a coffee cup. Right, and so this is a picture of a cute little coffee cup you can pick out at CERN, and the symbols, they might feel all a little bit odd and strange, but why don't we just kind of take this picture of the Lagrangian on the coffee cup and talk a little bit about what those terms mean. You don't need to know the details. You just need to know that these terms mean this kind of thing, right? And it's the same kind of Lagrangian that you're used to in your kinematics class, okay? It's just a Lagrangian density. So L equals kinetics minus potential, right? The first term, it's describing like force carriers. And so inside is like the physics of electrodynamics, the photons, and inside there also is some W and Z boson stuff. The very next line below it is how all that stuff interacts with each other. So how do photons interact with quarks? How do photons interact with leptons? Gluons, how do they interact with quarks? It all sits in that second line. You'll notice there's this cute little HC there, that's for Hermitian conjugate. And all that means is we need our Lagrangian to be Hermitian. And that means that all the observables that we get out of it are real. And so that's all that reason that it's there is to make the whole thing Hermitian, so we have real observables. The next line down is describing interactions between matter fields and the Higgs field, okay? And again, you don't need to look at the symbols and say, wow, I really understand those. You just need to know that that's what the line does. And then the very next final line is actually describing the Higgs sector itself. And what you notice is like in a standard Lagrangian, you have L equals T minus V, right? And so the V in this case, the potential is the potential of the universe, and that's the Higgs field. So it turns out that we have a certain base level of potential energy in the universe, the vacuum expectation energy. And that's the Higgs field, okay? So experimental particle physicists don't like writing Lagrangians. We like Feynman diagrams. We're simple folk. And so what you can do is you can match up the Lagrangian terms that you're seeing in the upper left-hand corner to Feynman diagrams. So if you see a term that's like 5 to the 4th, like you see on the left-hand side of this diagram cheat sheet, that is the same as you can see in that potential V phi term. And that corresponds to 2 scalar fields interacting and producing 2 more scalar fields. Similarly, in the middle, you have 2 Feynman fields or fermionic fields interacting with a scalar field. So this is like a Higgs decaying to a couple of quarks. And then the theorem on the right is an example of self-interaction. Okay, so like a Higgs can actually produce two Higgs. I know that's weird, right? But you guys are all used to quantum mechanics at this point. And so again, try to go back to like what we used to talk about back in the days of 453, which is it's all waves on water, right? And so all this means is you got a little wave in a scalar field, and that suddenly produces two waves in the scalar field. Makes you feel a little bit better than the idea of billiard balls. Okay, so with these Feynman diagrams, what it really makes us kind of simplify the job of an experimental particle physicist, which means that you're basically taking all the fundamental stuff on the left and you're trying to understand how it interacts with each other. And we do that via Feynman diagrams, which you can see on the right. And then each of those diagrams has a certain probability or cross section to happen. And it's all cross sections, all cross sections. That's all we're ever doing is cross sections, okay? And so we're just saying, how likely are they to interact? And the word cross section often is interplayed with different types of words like coupling. How strong does the Higgs field couple to the fermionic field? And that's what determines how probabilistic some interaction will be. But this is it. What you're seeing on the right, all we're doing at the LHC or really anywhere else is trying to figure out what all these different couplings are, what all these different strengths are, and then looking for new pieces of the puzzle, new stuff that's on the left. So if I go to the next slide here, what you see is on the very left side on the y-axis, this is the cross section, okay? So these are the different cross sections, and on the bottom axis across from left to right, you're seeing all these different processes that can happen. So how often do protons interact? That's the very leftmost column, and that has a particular cross section. And as you go from left to right, you see that things get more rare and very difficult to find. Okay, and the LHC's job is basically just to take all the spots in theory that we predict all these things to happen, which is those little gray lines across each one of them, and make a measurement and see if our measurements agree with theory. And so the blue, the orange, and the magenta are three different types of data, different energy that we've taken, and they're telling us roughly how well the experimental result agrees with the theoretical result. And that's it. The work that we'll talk about today is more connected with my group. And so what we mostly do is Higgs physics. And I think I'll talk about just one of these things to save some time. But the two big things that we've been involved with within the last couple of years are looking for how Higgs couples to fermions, okay? In particular, how Higgs couples to top quarks. And then looking at how a Higgs actually interacts with itself, okay? And that's the bottom left. So it's the top left and the bottom left Feynman diagrams that we're really looking at. The way that you have to get about any of this stuff, well, it's all requires a ridiculous amount of energy. You have to remember that all of this stuff played a really big role in, well, the Higgs plays a big role no matter what you're doing because it's a force carrier. But to actually get particle manifestations of these things, you need a ridiculous amount of energy. And to do that, we use the LHC, okay? The LHC is a glorified rock crusher, or collision of rocks. Right? We're doing the same thing we've always done, is throw stuff together and look at the pieces. So the LHC is about 16, 17 miles around. It is underneath the border between Switzerland and France. Basically, for most of that 16, 17 miles, you see a picture of what that looks like in the lower right-hand corner. It's just a big, long tube that goes around and around for a very long time. Okay. It accelerates protons in one direction, accelerates protons in another direction in a separate pipe. And when they, in a few spots, we cross those beams, we cross the pipes. And at those spots, the particles collide and we build big detectors around them to see what happens. So in this case, you can see that there's 4 of them, LHCb, CMS, ATLAS, and ALICE. The one that we work on in Michigan is the ATLAS experiment, which you can see kind of in the middle. The ATLAS experiment, it's a little bit hard to show pictures of. It's because it's this kind of deep cavern. And inside the deep cavern, once you go down there, it's like you're standing right next to it. So it's a little bit like trying to get the idea of how big a building is when you're standing right next to it. So we use this little graphic to kind of show. So it's about 7 stories high. You can see the little people that are, to give you the kind of the scale of the thing. And it's a sequential detector, meaning the stuff in the very middle is meant to detect particles that are certain type of particles, like charged particles, electrons, leptons, things like that. And then as you go outwards, you have different layers of detector meant to build different, or to detect different things. And the idea is that when there's a collision, you want to detect all the stuff that comes off it and be able to work all that stuff back and say, this is what happened at this point, okay? And so that's it. It's just sequential layers of different types of detectors over and over again. This picture, I think all of you have seen. In fact, I'm pretty sure that of this picture is, well, you probably haven't seen it in a year, since none of us have actually seen the department in a year, but this is hanging around at some point. So this is the looking right down the center of the ATLAS experiment, where the actual center of the thing was pulled out for maintenance. Okay, and then I have just a cute little video that just pulls this all together. Whoops. All right, so this is just protons zipping around different stages of the LHC to make the protons accelerate faster and faster. By the time they're getting to this phase, they're really at the speed of light, roughly, and so really you're just giving them energy, so effectively mass. Spinning around more and more, and then I wonder how much money the CERN spends on this kind of stuff. The animations, I mean. Okay, so protons going down the pipe, and there's a proton with 3 quarks in it. And then at the very middle of the ATLAS experiment, you can see what happens. There's a collision. All sorts of particles spray apart, and those layers of detector pick up all the different types of stuff that comes out of that. And from there, what you hope to do is be able to work your way backwards to see, okay, this is what kind of occurred in that area. These collisions happen 1 billion times a second. So it's a ridiculous amount of information and data that needs to be sifted through, and most of it we throw out because it's useless. So a lot of this type of work is being able to quickly decide what's useful and what's not useful, and then pull tiny amounts of important information out of a lot of data. This is what a collision looks like. In fact, this is a pretty typical collision. This is mostly hadronic. So what you're seeing here is 2 protons collide, and then you just get this spray of junk. Okay, so protons and neutrons and all sorts of stuff. And as they're flying along, if they're free quarks, they start ripping other stuff out of the vacuum to make this shower of particles called jets. And that's what you're looking at here is this shower of particle that's called jets. All right, so now back to the actual physics of the thing. The thing that I'll talk about today to give you a sense of what this kind of work is like is the Higgs coupling to top quarks. So how does the Higgs interact with top quarks? The reason we care about this is the Higgs looks at, I mean, it's kind of a cool concept in a way. So if I had the more and more charge I have, right, the stronger that the electric field would interact with that charge. And the idea of the Higgs is the more massive something is, the more, that means the more interaction the Higgs wants to interact with it. Well, the top quark is the most massive fundamental particle by far. It's about the weight of a silver atom, okay? So about the mass of a silver atom. So the Higgs loves it the best, absolutely loves it. So it becomes really important to actually probe around that coupling, okay? See if it interacts in exactly the way that we predict, or is there new physics that's there that totally throws all this off? The hard part about this is that, oh, and let me go down here. So this is what we're trying to look for is in the lower left-hand corner. So we're looking for studying how Higgs and tops interact. The way that we do this is when we collide protons, it turns out at the energy that we collide them, that it's not the quarks inside that interact, but it's this gluey mess of gluons that interact with each other most of the time. And so what you see here on the lower left-hand corner is 2 gluons that split into a couple of top quarks, all right? And then the top quarks from that splitting actually interact together and produce a Higgs boson. And so you see this Higgs boson right down the middle coming from two top quarks that are interacting. What comes along with this is whenever you create matter, you have to create antimatter, all right? So you have to balance that out. So these gluons, they split. One of them makes a top quark, the other one makes an anti-top quark. And so what comes with this is you see a Higgs boson and two top quarks, which is great and beautiful. At the same time, it requires a ridiculous amount of energy. And so these happen very, very rarely. And on top of that, because when they interact and they produce this kind of shower of crap everywhere, it makes it really hard for us to be able to say, all right, this stuff is actually a kind of event that we're looking at, and this over here is just junk. It turns out a lot of the times the junk looks like the thing that we're interested in. To give a scale of things for you, this type of process that we're looking for has a cross section that's roughly at where that blue line is that I'm showing, okay? So it's that really, really low line, about 500 femtobarns or so. So it's a very, very rare process. Okay. Once we have that, though, we don't actually directly detect top quarks and Higgs. These things actually decay into other particles, and we detect their remnants. And then from that, we infer back to what exactly happened. So Higgs decays to all these different things that you see on the right-hand side pie chart. And you might say at first glance that, like, okay, clearly you're going to look for Higgs going to Bs. To B quarks. Unfortunately, that is absolutely buried by background. It's very, very hard to pull those types of events from the big giant mess that is produced there. So protons are big giant garbage cans of stuff. And so when you interact with them, all these hadronic particles fly off everywhere. You get all sorts of quarks, and it just makes it really hard to distinguish those things from anything else that has a lot of quarks in it, like Higgs going to Bs. It turns out, which was kind of the key to the success of this particular analysis, is that you don't choose the Bs, you don't choose the Ws, the gluons, the taus. You look for Higgs going to photons, which is in that other 1%, which is incredibly rare, even more rare than the TTH on top that is there. But and even though it's very, very rare, it has a very clean signature. So we can really get rid of all that extra junk that we don't want and focus only on the stuff that we do, which is Higgs to photons. Okay, so now that we have that, this is what a TTH event looks like on the left-hand side. And the only other thing to do is to worry about how the top quarks decay. Don't worry too much about the details here. Just note the top quarks can decay so that you have nothing but quarks coming out, so jets of hadrons. Or you can have a situation where one of them decays like that, but the other one decays with a lepton involved. And the only reason we separate those two out is they have very different backgrounds, so we treat them differently. It's kind of a data analysis thing. So what you see here at the bottom is those two types of events. Ones where they have a lepton and ones where they don't. And we separate those types of events out so we get a little better sensitivity. We can treat them separately. Unfortunately, a lot of stuff mimics those types of events that you see in the lower left-hand corner. So we can't, like, with certainty say this is the type of event we're interested in. So top quarks often will just produce photons that radiate off them, right? And those can get mixed up with the events that we're looking for. Higgs bosons can be produced with photons that have nothing to do with top quarks, but since if you have a whole bunch of crap out there, maybe you accidentally think you see a top quark when there really isn't one there. And then you can actually produce tops and Higgs only in a way that actually where the Higgs isn't directly coupling to the top, or in a way that you can actually see that. And believe it or not, that's background. That's useless to us, because even though it's engaging in the process we're interested in, we can't measure anything from it. So this is the real rough part of this type of work, is being able to take this huge amount of background that we have and push it to the side and say, here are the only few things that I'm really excited about. The way we do that is you take all these events and you start looking at properties of all these events. And so what you see here are kinematics of many, many events. So what you can imagine is say you have 1 million events, and what you're going that satisfy some initial requirements that roughly look like the events we're interested in. And then we say, all right, well, for the stuff that I'm interested in, what does the photon's energy look like? And you can see that in the upper left-hand plot here. So the leading photon's energy, I can plot that for the stuff that I want, which is the red plot, that's TTH. And I can plot it for backgrounds. In this particular case, we use a control region in data where we just know that there's no TTH there. It's just full of a bunch of junk that looks like the stuff that we would get in the signal region. And you make all sorts of different cute plots like that. You look at leading photon energy, you look at leading jets, as many as you possibly can. Any way to be able to say, this particular variable has discriminating power between background and signal, okay? The next step of this is to try to take all of this and use it in some way. A long time ago, what we used to do is just do basically a cut and count, meaning that in each one of these little plots, you just make a cut. And you'd say, how often do I see the good stuff on the right versus the bad stuff on the left, or vice versa? And that would help us try to discern out from that, like how often we're getting the stuff we want and don't want. And we can measure a cross section from that. That is a very old way of doing things and is not really done anymore. What is done is taking all of this information and training some type of machine learning technique. And so it's been a very long time now since I've done an analysis where there has been no machine learning. It's ubiquitous now. And I put a little cute article here to talk about how some of this started up. It's from July in 2017, but to be honest, machine learning really cut its teeth probably way back in the early 2000s. And that's when it really was starting to come around. I can remember back then people were really worried about it because it was very much like a black box. And how can you really know what goes on inside that black box? But since then, now it's considered standard procedure for just about everything. The way it works is, well, they work in all sorts of different ways, but the simple way that this works is, as an example I'm giving is like a decision tree. And that means that you take an event and you say like, all right, what does this thing look like? And as an example, since we're talking about neural networks and stuff like that, right? So neurons like your head. This slide's a little old, so my son does no longer eating cell phones, but there was a day. So you can imagine like, okay, how does somebody actually make a decision on whether or not something is food or not food, right? And so you can imagine it's a series of questions that get answered. So the thing I'm looking at, does it look like food? Okay, does it smell like food? Does it pass all those properties? Same thing with an event. You can say, is this event really high energy? Okay, does the event have a lot of forward jets? Does it have a lepton? So on. You make all these kind of decisions, and at the very end, you assign a probability based on those decisions that the thing is the actual thing that you're excited about, or isn't. And this animation is not very useful, but I felt like since I have an animation, I should use it. And it says cat at the end, which doesn't help me. So we're all friends here. Okay, at the end of all of this, then what you get is you want to actually test to see how good does this thing do at being able to distinguish the thing that I want versus the thing that I don't want. And that's what you're looking at is just, all I'm doing is taking equal numbers of things that I want and equal numbers of things that I don't want and testing the thing out. So you can imagine I have a bunch of simulated events of the stuff that I want and a bunch of simulated events of the stuff that I don't want. And I keep throwing it at whatever I'm looking at. In this case, my boosted decision tree. So that's my machine learning algorithm. And this shows me that like the red stuff all ends up on the left and the blue stuff all ends up on the right. It does a really good job of separating out stuff I want, the blue, and the stuff that I don't want, the red. Okay. That's basically what you want this thing to do, okay? And this is really good separation. Sometimes they're not all this way. They can bleed over a lot more and you can get more difficult separation. This right here is the key though. So you can see this is really great discrimination, right? It does this really great job of separating things and you can say, ah, yeah, the signal's over here, the background's over here. But if you go back to some of these plots that we had before with just the regular kinematics, you'll notice it's not so easy to, in those distributions, to say where the signal is and where it isn't. This is the beauty of machine learning, is it can wrap up all this kinematics into one thing and use them all kind of together to say something very powerful, like this. Okay, so the analysis then takes all these distributions like we were looking at and feeds them into trees, into boosted decision trees. So if you remember way back, we talked about how we take Higgs events and we separate them into all jets or one where there's a lepton, right? And so that's what the top and the bottom here are, is that the top is all jets and the bottom is when there happens to be a lepton present. So we're just separating out events that have different backgrounds. On the left-hand side, you can see all the kinematics. They all get fed into a boosted decision tree, like the one we just showed, that's really good at separating backgrounds and signal. And then on the right-hand side, you can see how they separated everything out. Don't worry about the fact that when you see on the right, that doesn't look like the plot we saw a couple slides ago. That's because I was just using an example from a couple slides ago. What you see on the right is basically the same idea. So see the red plot? The red is the stuff that we want, okay? And the black and the blue is stuff that we don't want. And so this tells us how well we're separating stuff out. It's not perfect, right? Not as perfect as what we were seeing before, but it does a pretty good job. All right, and then the top one and the bottom one are just separately for that hadronic and the one with leptons. You can see here that like once I get past a certain level of whatever the BDT output is, right? You can think of this as kind of like a probability that the thing is signal or not. But once I get up to a BDT output of like 0.9 or less, all that stuff is background and junk. So you can imagine, like, I'm not going to look at any of that stuff because it's all background. So I'm just going to get rid of it. And say the same thing for the bottom one. At around 0.7, all the stuff that's behind it, 0.6, 0.5, is all junk, and I don't care about it. So I'm going to get rid of that. And I'm going to focus on just those little ranges where I think I have good signal to background. Okay, so all this is these plots are now zoomed in versions of that from 0.9 to 1 and 0.7 to 1, okay? And what we do is inside of these regions, to get even more sensitivity, we cut them up, okay? And the reason we cut up these regions is they have different signal to background ratios. And so we can kind of focus in those regions with different signal to background ratios to do individual modeling a little bit better, okay? And again, don't worry so much about the complications. The only thing you have to really worry about is like, all I did was I took a bunch of things that are sensitive differently to signal and background. I threw them into a BDT. It made some kind of discriminating distribution. And now inside that discriminating distribution, I'm breaking that up into little buckets that some have more background than others. That's it. That's all we've done here. All right. Now with those, I form these buckets. So you can see that I formed 4 buckets in the top all hadronic area and 3 buckets in the bottom. The only difference between the buckets is they have different signal to background ratios. That's it. And then inside each one of those buckets, what I do is I look at the events inside and I look at the 2 photons, all right, the 2 photons that are in those events. And I say, what's the invariant mass of those 2 photons? And if the invariant mass is very close to the Higgs mass, I can be pretty happy that that looks like a really good Higgs event. If it's not, I think, okay, that probably means it's a background. And so I plot inside those categories all the events that are in each category, and I say, in this category, and so here you can see the upper right-hand corner is the HAD3 category, right? So that's the second one from the right and the top one. Or I'm sorry, second one from the left and the top one. So that's what these events are. I plot the mass, and then from there, I fit, okay? I fit a bump with a functional form that's gonna look like Higgs events, and I fit a nice falling distribution that looks like the backgrounds. Don't worry about where we got them from. Just note that like we already knew ahead of time that the mass had that kind of form, that for the Higgs, it had a bump, and for the background, it was flat. So we do a fit. We do a big fit that fits that bump and fits the flat part. And that tells us inside that little region, that had 3 region, how many Higgs events do we get? And then we do that for every region. So that's what this looks like. Start from, this is can be confusing. So start from the bottom. Those are the regions that have the BDT output like we talked about, okay? Those all get cut up, and then in each one of those regions, we do a mass fit, okay? So we fit to the Higgs mass in every one of those regions, and that tells us roughly how much signal we have in each one of those, which feeds into the very plot at the top and shows us how much of the red that we want, okay? That's how much we're actually getting, how much TTH. We take that, with that, we add in all together, all of those little mass plots into one big mass plot, and you get this nice big clear bump. And this shows us that yes, indeed, we have a Higgs boson in these events with many, many top quarks. And this is the plot where we announced the observation. And we measure a cross section. Remember, a cross section is just a probability that we're able to actually get one of these types of events at the LHC. So we can tell that based on the efficiency of all the data that we got rid of. And then on top of that, the fit of our signal, that bump to the background on top. We're not the only group that's doing this kind of work. And so we're looking particularly at Higgs and photons, but Higgs decays to a lot of different things like we mentioned. And so there's other groups that do that. And you can see here that these lines at the top of the table like this going down are 3 different analyses that are also doing this, okay? And you can take all of these and say, yeah, I found this much Higgs, yeah, I found this much Higgs, add them all together, and that's the combined one at second from the bottom that says 670, and and that has 5.8 sigma in terms of it's 5.8 sigma significant over the null signal, okay, or not having anything at all. So this is the observation of this very important process that people have been working on for a couple of decades, actually. And you can see that 670 should be compared to the standard model prediction, the theoretical stuff, right? From the Lagrangian all the way back. That's just one step below 507. So you can see that we see a little bit more than we thought we should, but not statistically significant enough. Okay, and then this is just to show that like this is all the press that happens. So you get all this blog stuff and so on, all the things that have like 4 or 5 viewers, right? So that's the most fame that physicists can ever hope to get. All right. So that's the analysis portion of a lot of the work that gets done in experimental particle physics. So if you're doing collider physics, you do spend a lot of time doing things like this, statistics, data analysis, and that kind of work, learning machine learning techniques. The next thing that we're trying to do is so the top middle one is what we did a measurement of, all right, is to actually see if we see that, and indeed we do. The one that we were doing next is the bottom left one, which is to look for Higgs decaying to 2 Higgs bosons. So that's self-coupling, which is a weird thing. Sorry, hold on just a second here. Okay. So with the self-coupling, the issue is, well, this is what it looks like. You can see here, if you remember, the TTH signal was 500 femtobarns. The Higgs to 2 Higgs signal is 33 femtobarns. So over an order of magnitude less. It's very, very hard to find, okay? This makes it a challenge, and we need a lot more data to be able to pull this signal out of the background. So much so that really we're talking about on the order of 3,000 inverse femtobarns. So what you see here, if you don't know what luminosity is, don't worry. This is basically a plot of how much data the ATLAS detector has collected. So in the beginning, we don't detect a lot. In the end, we detect a lot more. You can see where we're at. We're at 2020. We're going to have to collect a lot more data before we have any hope of seeing that Higgs go to 2 Higgs, all right, and really studying that self-coupling mechanism. And so, in fact, we don't really even get there until get to a hope of it until like 2037, which is ridiculous, right? I'll be in a walker or something by then. Not that I'm not close to getting a walker already. Okay, to get those, the issue with all of that additional data that we're getting is that we really have to ramp up the collision rate. Okay, we have to make it a lot more intense. If you remember, we talked about 1 billion collisions per second. We have to make it even worse. So even more collisions means that these pictures like this get even more messy for us to be able to figure out what exactly is going on. And so maybe a good way to show it is like this is a simulation of an interaction on the left-hand side. This is for just one event. So a set of protons colliding with another protons. And you can see all the little yellow dots. Each one of those is an interaction within that one event. So when the LHC is really up and at its highest peak, when we upgrade it, they'll have over 200 interactions in just a single collision. It is really hard to be able to discern out from all those single interactions which ones are great and I'm excited about and which ones are not. Most of the time, it just is a bunch of noise. To be able to do that, we need to actually upgrade the machine. And so this is where the second part of this kind of job comes in. So the first part was data analysis work, things, machine learning, stuff like that. The second part is the hardware part, where we're actually upgrading components of the detector. There's two parts, or two things that Michigan is really big in muons. So some of you already know this already, but we do a lot with the Muon spectrometer, and that's everything that's in the upper left-hand corner that's in that kind of shaded blue, all right? The first thing that we're doing is we're building an entire new detector wheel, and that's what this thing is. And the only point of this thing is it's able to handle higher rates of particles coming at it, both by detecting them, but also surviving, because it's a lot of radiation. And so a lot of the electronics and detectors will die after a period of time, too much radiation. So they need to be more radiation hard and faster. So this is an active project that's going on right now, and they're building this. And so each one of these little sectors is actually 2 different technologies of detector that's put together. And as you know, when you ever see these detector technologies, it's easy to get kind of confused because there's a lot of different detector technologies. But note that ultimately it's always the same thing, right? You fill something with gas, and then you put a voltage on it, and when a particle goes through, it releases a bunch of electrons, ionizes the gas, and then that voltage pulls them to one side, and you get a signal. And we do that in just a lot of different ways to get more accuracy and or faster precision. And that's all that these 2 things are doing, is they're just doing it in 2 different ways. One of them sees signals much quicker and tells you that there's something there, and the other one is more accurate about telling you where exactly it hit. On top of that, each one of those detectors, you have to have electronics to read that out, okay? And the upper left-hand corner, you don't need to worry about the details at all. Only know that there's a bunch of electronics that are responsible for reading out that information from the detector, but also sending it off the detector. Everything that's in that little red dash, I guess it's not dash, crayon-y thing, is pieces that have been already built at Michigan. So Junji, Zhu, and myself are involved in this. And so we built a lot of high-speed electronics. The way that this works for physicists, so this is what those look like, by the way. So the lower left-hand is the board that we built. By the way, I spent a little extra money to make these boards blue, just because I wanted it all to be Michigan. You can see the Michigan symbol on that. Don't tell the NSF about that. And the upper right-hand corner, you can see the design of the thing. as physicists, you guys rarely do the kind of work that's in the upper right-hand corner, okay? That's an engineer. And so we have an engineer who does all this kind of design. What a physicist does is often like helps in determining how that design is going, or what is needed out of that design, and then tests these boards. So a lot of undergraduates will do research in terms of just taking a bunch of these boards that are produced and testing them on detectors, but also just making sure that the ones that we produce are okay. There's more to it than that. And so as an example, you have to make sure that these boards can survive in a very high radiation environment for a long period of time. And so we do a lot of testing of radiation. And this is something that undergrads have stepped in a lot and helped out a lot in. And so you can see here in the upper left-hand corner, this was a test that we did on the board that you saw at the Democritos facility in Athens. We irradiated it for a long period of time and just see how the board works in that kind of environment. Does it survive? In the lower right-hand corner, we have a really good relationship with the Lance facility. This is at Los Alamos. It's a weapons testing facility for neutrons. We use it for our purposes, and we just hit it with a bunch of neutrons and see, okay, how does our board react under those kinds of circumstances? And another thing that undergrads will do is, for example, actually, I think Sabrina, you did this, right? Did you take the boards to B&L?
No, I
You weren't involved.
Never got to go. I know
Okay.
the other undergrads did go when I was in it.
I know that there's an undergrad that did this. So, so at Brookhaven, we have a cobalt-60 source, and we took the board and brought it into a cobalt-60 source, and you basically just try to kill it. And so you irradiate it as absolutely much as possible, and you say, how much radiation can this thing take before it's dead? And so that's another thing, and that's a great project for undergraduate students. You guys are all really quite bright, and so you just program up little GUIs, see what the operation is, and then basically put it in front of a nasty source and wait till it dies and tell me how much radiation it took before it dies. And that's a great project for undergraduate students. So many of them have done that kind of work. The other project here at Michigan is the next phase of this, which is basically upgrading the other parts of the Muon spectrometer, which is everything in blue, all the stuff in blue. And so we're building a bunch of new detectors like you see in the lower right-hand corner. And we're on top of that, we're replacing all the electronics that are associated with this. These devices are simple. They're just gas filled. There's a wire that goes down the middle and a voltage from the wire to the outside. When a muon goes through, it ionizes the gas on the inside, and that's picked up by the wire. And then based on which tubes and where it hit, we can figure out a nice cute track that goes through. And this is a video that shows you kind of how that works. Sorry for the grainy video. This is the best I could do. That guy is just sitting there on the top. I didn't see that before. Okay, so this is all the pieces of the muon spectrometer. They're kind of separated away. Inside each one of these is all these little sets of tubes. So there they are. Okay, they're all glued together. That's basically it. A precision glue gun is what's used. Particle goes through, ionizes the gas. The voltage, the potential between the outside and the inside sucks over the charge, and you can tell where exactly the track went. And then you have enough of these chambers where you can actually just kind of connect the dots. And there you have it. And that's how the thing works in a nutshell. The difficult part, of course, is to do this precisely and to be able to do it so that they can read out very, very quickly. Whoops. Okay. And on the lower right-hand corner, this work actually happens in Michigan, so in the high bay. And so this is one of the chambers that's being built down there right now. Well, this was an old one that we built a while ago. So we are building these things right now, and actually this is a good opportunity for undergraduates to work on constructing detectors. There's a lot of of work that needs to be done in that regard. Outside of that, there is a bunch of electronics work that's going on. And so all I've done is take that cute little detector and moved it in the upper right-hand corner and then strung together a bunch of little blocks that represent electronics boards that are part of the readout. Don't worry about the details, just note that we have to build a bunch of electronics boards to read everything out. And Michigan is doing the entire front end, basically. And so what you see here is the boards that we're building on the left-hand side. Genji's building some chips, and you can see the design of that in the middle. And then we build detectors on the right. We're basically that entire chain. And so what's cool about that is this is kind of we're the only undergrad institution, or the only university institution, I believe, that's building detectors for this. And then on top of that, we have the readout electronics. So you can basically do all this R&D in just one site, which is really rare. And so it's a really cool thing to be able to, for students to be able to see like kind of that full chain. That doesn't happen very often. Okay. So that's basically the type of work that is done in a nutshell, okay? And there's a lot of activity in the ATLAS group. So there's a lot of data analysis work that gets done. We talked about the Higgs today, but there's more than that. And so here at Michigan, we do pretty much everything but B physics. And so you're searching for new particles, searching for dark matter, doing precision measurements of the standard model. The sky's kind of the limit. That's mostly because there's just a lot of faculty doing this. There's a lot of hardware work. You can build particle detectors, test high-speed electronics, do radiation testing, installation and commissioning on the actual ATLAS detector. So actually building things and putting them on the detector. And we hire a lot of undergraduate researchers, and you get a lot of skills and things like data analysis, data science, programming, high-speed electronics, particle detectors, radiation. If you're interested in those kind of opportunities, you should reach out to any of the ATLAS faculty. I unfortunately am not taking on any students right now, but there's 4 other faculty that are involved with this. And so we're almost always, or periodically, we're always looking for somebody, right? And so and this is good work to get involved in. Okay. So that's it for the science part of the talk. After that, I thought, based on what Kevin and I were talking about, doing some topics of discussion, but maybe we'll go to that next and first see if anybody has any questions about the talk.